Okay. So if you remember back to earlier today, there was this one slide that was kind of snuck in the middle of the slide deck about, well, how do you use OpenMP? And it went through these steps as the basic approach, which is to say, find your compute-intensive loops that are good candidates for parallelism. And then make the loop iterations independent so that they can safely execute in any order without those loop-carried dependencies. And then, after you've done that, place the appropriate OpenMP directives into your code. Well, I actually helped write these slides, but when I was writing them, a cartoon came to mind. And in order to avoid copyrights, I didn't paste it into the slide deck, but if you want to Google for "Then a Miracle Occurs" cartoon, you can probably bring up something that's very familiar to you. It's a very famous cartoon by a mathematician who's writing on the blackboard, writes some great starting equations, and then in the end he says, therefore it's true, and in the middle is this cloud saying, well, then a miracle happens. Well, parallel programming can be a little bit like that to a lot of people, and those little red sections up there are sort of where the miracle happens. And the question is, what can you do about that? Is it always going to be hard? Is it always going to be tedious? If you take the OpenMP examples that I gave you and just sit down in your favorite editor and look at them and stare at them, that's exactly where you are. You're in the then a miracle happens stage. So several years ago, I said, we've got to be able to do something better about this particular problem. When I was in grad school, I was working on automatic parallelizing compilers. I said, oh, that's got to be the answer to it. Well, it turns out it was not the answer. We made really great automatic parallel compilers. They were world-class, and none of the customers liked them because they were these magic tools that one day they would work wonderfully. You fix a bug, edit your code, the next day they stop working because you changed the dependence pattern in your code, you made it more complex. All of a sudden, the compiler couldn't figure out your code, and all of a sudden, it does nothing. So I switched strategies to say, well, the smartest thing in the room is the programmer, so how do we get the programmers more involved and give them tools to make smarter decisions? So one of the things we started thinking about is how do you create programs? How do you even create parallel programs? And do they just magically spring out of your head in parallel form and you just write them down and everything's easy? Well, if that was true, basically where do you start? So if you have the luxury of sitting in the corner thinking to yourself and just, I'm going to write something new, maybe you do have a blank sheet of paper in front of you and you can just write down whatever you want on that sheet of paper. I would wager what you write down on that sheet of paper is not a parallel algorithm when you're solving a new problem. You're writing down a series of steps, maybe a few formulas. You're going to debug your formulas, try to figure out if they work, and your first prototype's probably going to be sequential. Because it's the simplest thing to think about. It's a series of steps that produces an answer you want to produce. But most of the time, you're working in an existing environment. You're working with code that might have been in existence longer than you've been alive. And someone says, this is valuable code. It produces a valuable answer. It just does it too slow. Make it run faster. Oh, and by the way, add this new feature while you're making it run faster. So I've talked to a few people and sort of introduced the concept, are we doing computer science or archaeology? Sometimes I'm not sure which one it is. A lot of times you're going in trying to reverse engineer a lot of code, which may or may not have been well written, well structured. It might have lots of hidden data structures and hidden assumptions in it that it's your job to figure out how to clean up, port to a new architecture, make run in parallel, etc. Or maybe your team's been working on this MPI code for years and it scales wonderfully. And then someone says, oh, but by the way, we now need to shrink its memory footprint because now the cores don't have as much memory. We need to introduce OpenMP into each rank of your MPI program because we wanted to use shared memory so that we don't have to replicate it so much. One of the ways is just take the place you've got it parallel already, and then strip mine that loop and put part of it at the MPI level, and then just have a little loop for OpenMP on the inner one. Or you might want to say, well, let's look at some of the algorithms that are currently running sequentially inside of each MPI rank and see if we can add a nested level of parallelism there. Well, each rank of your MPI program is just a serial program. So you're really starting from the same place, whether you wanted to or not. So except in some very rare cases, you're sort of starting from a serial point when you're trying to introduce things, especially with the OpenMP. So let's talk a little bit about what that sort of means to start from a serial program. So here's some examples at the top of the screen of little serial loops. And you may have written loops like this, and the question is, when you wrote this loop or when you read it, what did you think it was? Did you think it was actually this series of steps at the bottom? Because that's actually what it means. That when you write that loop, it says, oh, you've got this control variable. You're going to execute the statement. You're going to increment the statement. You're going to branch somewhere else. You're going to do it again. It's a very sequential set of steps. And for when the compiler sees that piece of code, that's exactly what it thinks it means. But maybe when you wrote that piece of code, you had something different in mind. Maybe you said, oh, well, it's just an idea of how I want this concept implemented, and there's other ways it could be implemented. Maybe it's sort of a way of expressing an array assignment because you don't have the syntax to express what you have in your head. Maybe it's kind of a little parallel-like for each loop where you don't have the syntax in your language, so instead you wrote it sequentially. Or maybe it's a combination of some kind of vector expression which launches data parallel tasks. But all of this is kind of your thought process of when you wrote down that piece of code or when somebody else wrote it down, did they actually mean, yes, this must be executed sequentially one step at a time? Or did they mean, well, I want this effect accomplished and I don't really care how it's accomplished? My guess is it's usually more like this. So one little digression about tools, and I think this has been fairly consistent when I've given this talk. What's the #1 debugging tool in the world? And no fair peeking ahead, it's printf. Everyone uses it. But the question is, why do you use it? It allows you to observe your code, usually without changing its behavior. Because you can generate a print statement to a file, it goes off on the side, maybe it slows it down a little bit, but you're not breaking your code by putting a bunch of print statements into it usually. So it's usually a safe thing to do, but you're doing it for observation because you want to observe what the code's doing internally. Well, we took this idea and we said, well, what if we could put print statements in there for other purposes, to observe other things that are going on in your code? So we invented a couple new kinds of print statements that behave a little bit like parallel programming language, but they're actually not. They're really just a set of sort of print statements you put in your code to annotate different parts of it. And we called these things a cite, a task, and a lock. And I'll go into a little detail about what these are and how they correspond to parallel languages and why you might want to consider using these before you use a parallel language and what you can do with them. So a cite just says, I want to focus on this part of my program. You might think of it a little bit like a parallel region we were talking about in OpenMP. It has the property outside of the cite, things are serial. Inside of the cite, maybe there's some parallelism going on, and we give it a name. And we're going to be using annotations or things that look like just function calls or macros you stick into your code, and you can think of these are just trace statements you're going to put into your code and says this block of code is where I'm interested, that's my cite. Similarly for task, if you say earlier we talked about OpenMP tasks, well, this is a more generalized concept that just says, well, this block of code I want to potentially assign to another processor, and I'm not going to worry about how it's implemented. The reality is, in this particular program, it's still running sequentially. It's not moved anywhere, but I'm just annotating what I want to do with it. And we have a similar syntax. You just put a call into your code saying, this is where I would like to propose putting a task in. And what we're doing here is creating a modeling language as opposed to an implementation language. This is kind of to express your thoughts of, well, what happens if I assign the work function to another processor. Is that going to be a good thing? Is that going to be a bad thing? Is it going to cause bugs in my program? Is it going to cause me to speed up? I don't know yet, but I think mathematically it should be kind of an interesting thing to consider doing. And then the last part of the modeling language is that sometimes you want to fix bugs or get closer to your implementation by saying, well, I don't want everything to just run in parallel. I want to synchronize some things. I want to model atomic sections. I want to model critical sections. I want to model locks. I want to model reductions. And those are, as you refine your model to get closer to reality and get ready to implement it in your favorite language, like OpenMP, you might want to annotate all these places where you have to pay attention to the synchronization. So we've got a couple pairs of statements, which is just annotate. Well, I want to serialize at this point by acquiring a lock and releasing a lock. And the address of the lock goes in the argument, and normally we just pass in 0, saying, well, it's just a global lock similar to an OMP critical. So the kind of question is, what can you do with this? Well, if you have a loop in your program that you say, well, I want to make this run in parallel, how would I model this loop? So on the right-hand side, this might be how you would express it with sort of OpenMP task. You say, create a parallel region for each, create a dispatch work sharing construct with a single, and then each iteration of my loop is going to be a task. Well, in the annotation modeling language, you do sort of the same thing, annotate the whole loop into a site, and then annotate the body of your loop into a task, and you spit off a bunch of tasks. So it's really a sort of a simplified version of the parallel language, and not that much more difficult to use. There's one special case we found out for optimization, which is that if you really do have a parallel loop, maybe you don't want to break up everything into tasks. You just want to say, partition everything that happens into this site into tasks implicitly by breaking it up at the iteration task boundary. So every time you see iteration task, it closes the old task and starts a new one and just breaks it up into chunks. So logically, you're creating a whole bunch of tasks by just partitioning that particular loop. Every iteration becomes a task. So the product that we installed, Parallel Studio 2013, includes a tool we just released about a year ago called Advisor XE. And it's a new class of tool. At least I think it's relatively new. There's been programming assistants that are compiler-based, which basically use a lot of static analysis to try to understand your program and give you advice about how to introduce things in. But this is one of the first one that's based on dynamic tools. And when you look at the hard problems in parallel programming, they usually have to do with complex control structures, complex data structures, and compilers are lousy at figuring those out. But if you do kind of runtime techniques, kind of dynamic analysis, dynamic simulation, all those things become easy to figure out. A little bit slow, but easy to figure out. So let's look and see what some of these tools are and how we're going to use them. So the tool not only is just a couple profilers or simulators, it also includes a workflow that tries to train people how do you write a parallel program. And as part of that workflow, you've got a choice as to how you're going to order your activities. And what we tell people when we teach them how to do with this is focus on performance first, not correctness. And sometimes I get really, really bad looks from people when I say that, because if your program's not correct, why are you writing it? Well, if all you care about is correctness, why are you parallelizing your code in the first place? You've already got a correct code sitting in front of you. It's your original sequential code. The only reason you want to go to parallelism is because you want it to run faster. Once it runs faster, you also need it to run correct. If there's no opportunity to get it to run faster, why are you investing all this effort into rewriting it? So what we do is we first try to estimate what's the plausible benefit from the model you want to introduce into your program, how much headroom is there, and if there's enough headroom so that the payoff is good enough, then we go in and investigate what is it going to take to make that particular model correct. Because you do have to get both of them right before you're done and have a correct program. But at least there has to be the opportunity to have sufficient parallelism. So this is the tool. If you do have VNC or other X Windows software and are able to source the path, if you type advisor XE, adv xi xe -GUI, you should get a window up on your screen that looks like this. On the left-hand side is the workflow. It's a 5-step workflow. It should be very similar to anyone who's done parallel programming. It basically says, profile your code to find out what's important. There's no point in adding parallelism to something that's not expensive. So find out what's important. 2, look at that place and create a model of what you would want to do. It doesn't have to be a good model. It doesn't have to be a correct model. It doesn't have to be anything. But you need to say, how do I want to break things up here? Do I want to break it up by iteration? Do I want to break it up by statement? Do I want to break it up by function call? Somehow you've got to say, this is what I think I can do here. Step 3 is check suitability, which is to say, what's the performance prediction for my model? If it's good, let's continue. If it's bad, let's go back and fix our model before we go any further and waste time. Step 4 is check correctness. This is a rather expensive tool that looks at every single memory reference your program makes and predicts where the data races are going to be in your program before it runs in parallel. That can basically tell you how much effort do you have to go in to restructure all of your data. Are you going to have to invent a new algorithm because everything's hopeless? This is giving you the feedback so that the developer can stay in charge. And then step 5 at the end, after you've iterated on the other steps, is given your model, which describes how to think about parallelism, then you get into the implementation phase of, well, how am I going to implement it? Am I going to change it into OpenMP like the construct we had earlier? Do I actually want to use MPI? There's no reason why you couldn't take the same modeling language and use MPI. Do I want to use OpenCL? Do I want to use Charm? You could switch it to anything. Once you know how to think about your program in parallel, how you actually implement and run it becomes a much easier problem because it's just syntax at that point. You've already solved all the hard problems of understanding how you're going to partition it, how you're going to change your data structures, how you're going to synchronize it. So this is the Pi example from the zip file that I pointed you at earlier. If you are able to run the tool on the example, it shows you the looping structure of the code so that now what the code's doing is visible. It's showing you how much time is spent inside of each loop, and it says this is a really easy problem to parallelize. The innermost loop has 100% of the execution time. That's really nice. That never happens in practice. So if you double click on that loop, it takes you to the source code. It's kind of blurry. It's supposed to be showing the source code. And then so it starts attributing times to the loops, and you can start thinking about, given this particular structure, given what it's trying to compute, is this a good place to partition and make run in parallel? And the good thing about modeling languages is it doesn't cost anything to be wrong. You say, well, sure, it's a great place to run in parallel. And you just put the pragmas in there, and then we can move on to the next step. So once you have your loop, then you say, well, let's start changing it to introduce the concepts of parallelism, not the implementation. So I say, well, I want to focus on this loop, so I wrap a site around it. And then I just want to split up all the iterations and let them run in parallel. So by putting 2 or 3 statements in, very similar to the kinds of things that you're eventually going to put in for OpenMP, you can teach the system that this is how you want to model your program, and then we can start running some tools on that model. So we can start looking at that particular model, looking at your data set, which you think is appropriate for production, and say, well, how big are the tasks that you just created? How many tasks are there? How many processors do you think you can spread them across? What's the cost for dispatching a task onto a CPU? And we start building up this picture, which looks a little bit like a speed-up graph. We've been calling it a maximum gain graph because it really is an idealized type of speed-up graph. And this says, for this particular program, if you actually execute it as you modeled it, it's horrible. There's a bunch of dots at the very bottom of the red line, which is if we were to actually execute it as we modeled it, we would get no speed up, we'd probably get a slowdown. And the reason for that is in our model we said every single iteration of that pi summation loop I want to assign to a separate thread, sort of using dynamic one scheduling on that loop. Each iteration is tiny. There's no way you'd have a successful implementation if you actually use dynamic one scheduling on that particular loop. You would just be swamped with overhead. But the tool has told us that there's a way to fix this. So in addition to modeling your model as you wrote it, it models variations of the model. And in particular, it looks at 5 different axes and says, well, what if the cost of doing certain things were cheaper? Would your model run better? Because it's trying to figure out a sensitivity analysis of your model to the different costs. So what if the cost of spawning a parallel region was 0? Would your model run any faster? What if the cost of launching a task was 0? Would it run any faster? What if you bundled all of your tasks into big chunks? Would it run any faster? And what it's saying here is that if we were to use task chunking, i.e. maybe static instead of dynamic, we would all of a sudden get a speed up of 7x on 8 cores instead of like 0.1x. So what it's identified is the size of your iterations is too small, but there's plenty of work in the entire loop if you just group your iterations together sufficiently. So using static scheduling, this has great potential. Using dynamic one scheduling, it has lousy potential. So what this tells us is our model's on track. We're going to have to pay attention to the scheduling of the loop to make sure that the granularity of the tasks we assign to the threads is big enough. But if we do, there's a lot of potential here. And again, there's a couple slides here talking about how this simulation works. And then we move on to the next step, which is we've got the potential in our model. And this is the step that usually kills projects. Like, it's pretty easy to figure out where your program's spending your time. It's not that hard to convince yourself that, yes, your tasks are big enough. What usually kills you are the data structures, because they're usually not simple like these examples we've got here. They're hairy hash tables, adaptive meshes, they're weird things that somebody optimized years ago. And how are you going to sort through all those pointers, sort through all that code? It might be buried in a bunch of libraries. Well, this particular tool does binary instrumentation of all of that mess, including handwritten assembly code as well as C code, tracks every single memory reference with respect to the model you wrote, and then tells you where your problems are. So in this particular example, it's pointed out that we have 2 different data communication problems that are potential in this model. But what it's telling us is in our pi example, as it's written, we have an x plus equals something and a sum plus equals something. And those are obviously cross-iteration data dependencies where one task is sending a value to another task. And it's pointing us to those lines of code saying, you better take care of this before you write your OpenMP code. It's identified, yes, this is a plausible candidate. It's told us where we need to work. It's not confused by pointers. It's not confused by millions of lines of code. It's not confused by other things. One thing it does require is you need a relatively small data set. Otherwise, you're going to be waiting forever for the simulation to finish. So when we set this up, the tool asks you actually to build 2 different binaries and to get 2 different data sets to use the tool. One of the binaries and data sets is basically a production-sized data set. Something relatively big so that when you profile it, the loops which are important in a production code are also important in your profile. It doesn't have to be huge, it just has to be representative so that it points at the right places. The other one is a debug build with the absolute smallest data set that will actually test your code. Instead of 1 million iterations, maybe it has 4 iterations. Something unbelievably tiny, because it's going to be checking every single memory reference anywhere in your code to see if it's legal. But you want enough iterations so that you're actually executing your code paths. If you've got different variants for different kinds of elements, different kinds of boundary conditions, it's got to be big enough to actually test that. But as long as it tests it 2 or 3 times, that's usually sufficient, and you can get a report like this that says, where are all of the potential problems? Again, talking about how it works. Once you've done this modeling, there's some fairly mechanical ways of deciding how you're going to change your model into your favorite parallel programming language. Like I was saying earlier, there's the kind of syntactic correspondence. We have documentation that shows some of the common patterns. And then you have your first parallel program, and now you need to figure out how does it map to the hardware. So you run it, you use a real profiler like vTune to figure out how well is it executing, how are the threads scheduled. Maybe your translation into the parallel language wasn't quite perfect, so we've got tools like Inspector, which again debug your program, look for your data races, look for your locking problems, and hopefully at the end of this, you've got a correctly functioning parallel program. The tools that I showed you here are designed to work on a standalone serial program and launched from the GUI. If you want to do this on a rank of your MPI program, there's command line tools that you can inject into your MPI run command, collect the results in the background running on a cluster, and then import the results into the GUI so you can see the same results on one of the ranks of your MPI program, if that's the serial program that you're working with. Normally you do this on a relatively small cluster. You don't use the big machines. You're trying to use this for software development, not for production, because you're trying to understand what's going on. So that's all I had for the tool introduction. If you're capable of using the tool, I can help walk through it and figure it out. Otherwise, you can try seeing what it's like writing a parallel program by hand without the tools. I find it's not nearly as much fun. One of the analogies that I give people sometimes is how much fun or how effective would it be to learn a new programming language if every time you make a mistake, the compiler segfaulted? Learning a new language would be miserable. So the availability tools and the quality of the tools you have dramatically affects your productivity and your ability to accomplish things. And tools like this that are available now are sort of like compilers that don't segfault. So thank you very much.